Greetings, I am just a fragment of imagination. But did you know that whenever electric current flows through a wire, something invisible forms around it? A magnetic field appears in the space surrounding that conductor. This magnetic effect is extremely important because it is the principle behind many electrical devices, such as motors, transformers, generators, and inductors. Understanding how magnetic fields interact with electric current allows us to understand how inductors behave in circuits, especially when connected to a DC power supply. Let us begin with the relationship between current and magnetic fields. When current flows through a conductor, circular magnetic flux lines form around the wire. The direction of these magnetic field lines can be determined using the right-hand rule. If you point your thumb in the direction of current flow, your fingers curl in the direction of the magnetic field. If the wire is wrapped into a coil, the magnetic fields from each loop combine together, creating a stronger magnetic field through the center of the coil. This coil of wire is called an inductor. An inductor is an electrical component designed to create and store energy in a magnetic field when current flows through it. The ability of the coil to generate this magnetic field is known as inductance. Inductance depends on several physical factors such as the number of turns in the coil, the cross-sectional area of the coil, the length of the coil, and the type of material used in the core. Increasing the number of turns or using a magnetic core can significantly increase the inductance and strengthen the magnetic field produced by the inductor. Inductors behave uniquely when the current in a circuit changes. According to Faraday's law of electromagnetic induction, when the magnetic flux through a coil changes with time, a voltage is induced across the coil. This induced voltage depends on how quickly the current through the coil changes. The equation gives the mathematical relationship describing this behavior. V equals L multiplied by di over dt. In this equation, V represents the voltage across the inductor, L represents the inductance, and di over dt represents the rate of change of current with respect to time. This equation shows that inductors react to changes in current rather than the current itself. Another important concept related to inductors is Lenz's law. Lenz's law states that the induced voltage in a coil always opposes the change in current that created it. In other words, an inductor resists sudden changes in current. If the current tries to increase quickly, the inductor generates a voltage that opposes that increase. If the current suddenly decreases, the inductor produces a voltage that attempts to maintain the current flow. Let us now consider how inductors behave when connected to a direct current source. In a simple RL circuit containing a resistor, an inductor, and a DC voltage source, the current does not instantly reach its maximum value when the switch is closed. At the exact moment the circuit is energized, the inductor opposes the sudden change in current and behaves like an open circuit. As time passes, the current gradually increases while the voltage across the inductor decreases. Eventually, the circuit reaches steady-state conditions where the current becomes constant. At this point, the rate of change of current becomes zero, meaning the voltage across the inductor also becomes zero. Therefore, under steady-state DC conditions, an ideal inductor behaves like a short circuit. Let us now look at an example of induced voltage in an inductor. Suppose an inductor has an inductance of 2 henries. The current through the inductor increases from 0 amperes to 4 amperes in 2 seconds. To determine the voltage induced across the inductor, we use the equation V equals L multiplied by di over dt. First, we calculate the rate of change of current. The current changes from 0 to 4 amperes in 2 seconds, which means the change in current divided by time is 4 divided by 2, or 2 amperes per second. Substituting the values into the equation gives V equals 2 multiplied by 2. Therefore, the induced voltage across the inductor is 4 volts. Another important property of inductors is their ability to store energy. Unlike resistors, which dissipate energy as heat, inductors store energy in the magnetic field created by the current flowing through the coil. The energy stored in an inductor depends on both the inductance and the current flowing through it. The equation for the energy stored in an inductor is W equals 1/2 multiplied by L multiplied by I squared. Let us consider another example. Suppose an inductor has an inductance of 3 henries and carries a current of 2 amperes. The energy stored in the magnetic field can be calculated using the formula W equals 1/2 multiplied by L multiplied by I squared. Substituting the values gives W equals 1/2 multiplied by 3 multiplied by 2 squared. 2 squared equals 4, and 1/2 multiplied by 3 multiplied by 4 equals 6 joules. Therefore, the inductor stores 6 joules of energy in its magnetic field. This stored energy can be released when the current in the circuit changes. For example, if the current suddenly stops, the collapsing magnetic field generates a voltage that attempts to keep the current flowing. This effect can produce very high voltages and is the reason sparks sometimes appear across switches when inductive circuits are opened. In summary, inductors are electrical components that store energy in magnetic fields and resist changes in current. When a DC voltage is first applied, the inductor initially opposes the current flow. Over time, the current increases until steady state is reached, at which point the inductor behaves like a short circuit. Through principles such as Faraday's law and Lenz's law, inductors play a crucial role in many electrical and electronic systems. Thank you for listening.